Okay, chapter 3, stacks and queues. And in chapter 2, we talked about arrays and structures. And these are quite simple data structures to have some information. Okay. And after that, I introduced the C++, especially class. And the class is another kind of data type to have some information in there with some member functions. Okay. So far we talked about general data types from the program languages. And from this chapter, we'll talk about some special data structures to have information. Okay. So the first chapter is stacks and queues. And the next we'll talk about the linked list and trees and graph and the hash and whatever. Okay. In this chapter, first we'll talk about stack as an abstract data type. Abstract data type means we have objects and operations, or data and functions, like a class. And we'll talk about queue as an abstract data type. And we have a couple of applications, amazing problem and evaluation of expressions like a calculator. Okay. And then we'll talk about multiple stacks and queues. Okay, first, what is a stack? Okay, stack is an ordered list in which insertion and deletion are made at one end called top. Okay, so you know what ordered list is, right? So it's something like an array. Okay, and the insertion and deletion are made at one end called top. So if you look at this figure on the right side, then you can figure out what I mean by this one end called top. So we have a stack, and then as you can see on the bottom, at the bottom of this slide, the stack has the one closed side and one open side. Okay, and all the operations are at the top of this stack, the open side. So when we add new element, then we will add new element through this open side. And when we delete, or when we get one element out of this stack, then we will get it through this, from this open side. Okay. And given a stack S from A naught to A sub n minus 1, A naught is the bottom element and A n minus 1 is the top element. So in this case, A naught is the first in. Okay. And then A sub n minus 1 is the last in. And the stack is kind of a LIFO structure. It means the last in will be the first out. So look at this figure one more time on the right side. So we have A, B, C, D in this stack. And we can see that the A was the first in, and the B is the second, then C, and then D. And D is the last input. Okay, when we delete, or when we take one element out of this stack, then the D will be the first element. Okay, that's what this last in first out means. Okay, this slide shows some real kind of example of stacks in our real life. The first one is coin case. Have you ever seen this coin case before? Okay, maybe not recently, but long time ago in the taxi, they had this coin case. Okay, so in this case, we push the new coins through this coin case, and then when we need a coin, then we will get one from this coin case. So think about this one. The last in will be the first out, right? And at the bottom of this coin case, we have the first in coin. That is the oldest coin here. Or look at this terrible parking lot. This is terrible parking lot, and the red SUV is the first in car, and the green car, and the white car, and then the red car again. And then when we pull these cars out of this parking lot, then this red car should be the first out, and then white one and green one, and then red SUV. So this is terrible parking lot, but sometimes we have this kind of parking lot. Okay, let's take an example of a stack to understand how it works. Okay, so basically, if we add elements A, B, C, D, E to the stack in that order, then these things will happen. So let's take a look at this graph. So first time we push, so we call it push, okay, instead of insert. Okay, when we push one element, the A is the first element, so when we push A, then we have only A in this stack, and the top is pointing A because A is at the top of this stack. And then next element is B. Okay, so we push B into this stack, and then top is pointing B because B is at the top of this stack. And again, we push C and D and E. Then the top increases as we push an element. Okay, now top is pointing E. Okay, and then if we pop means we take one element out of this stack. So if we pop, then E will be the first out. And then, whenever we take one element out of this stack, then the top decreases because we lost E, right? So we don't have E anymore in this stack. So top is pointing D because D is at the top of this stack. Okay. Okay, here is another example of a stack, which is in the computer systems actually. And do you remember when I explained the memory structures with the stack and the heap? So basically, whenever we call a function, then the local variables, the memory space for the local variables are allocated from the stack. And whenever we call the malloc, then the memory space will be allocated from the heap. Okay, and the reason why we call the stack is that it is actually a stack here. Okay, so this tag will have more than just return address, but to make the explanation simpler, let's assume that we keep this return address in the stack. Okay, so this explanation, this slide is way much simplified version of the real system stack. Okay, so we have a function 1. Okay, so in the middle of this function 1, then we have function 2. So function 1 is calling function 2. So when the function 2 is done, when we finish function 2, then we have to come back to the next line 1, right? So we have to keep this information, the address of this next line 1 somewhere. Okay, then in the function 2, it calls function 3. It means when we are done with the function 3, then we have to come back to the next line 2. Okay, so we need to keep the address of next line 2. And also in the function 3, we call function 4. It means we have to keep the address of next line 3. Okay, then when we are done with the function 4, then we can come back. So how can we manage these all the informations, the address of next line 1 and address of next line 2 and address of next line 3? So the stack is the best data structure to handle this kind of informations. Okay, so the next line 1 is the first input. Okay, so when we call the function 2, then we push the address of next line 1. So don't get me wrong with these figures. So in this stack, we have next line 1 and next line 2 and 3, but actually the address of next line 1 will go into this stack. Okay, so when we call function 2, then we push the address of next line 1 into our stack. So now we have next line 1 at the top of this stack. Good. Then in the function 2, when we call function 3, then we push the address of next line 2 into the stack. Okay, now at the top of this stack we have next line 2. And in function 3, when we call function 4, then we push the address of next line 3 into our stack. Okay, so we have all the informations, and when we are done with this function 4, then how do we know where to go? Okay, the stack has the information, so we take one information out of this stack. that's the address of next line 3. That's where to go actually. So based on this information, we can come back to the next line 3. Okay, then when we are done with this function 3, then how do we know where to go? So we pop one element from the stack, which is the address of next line 2. So we can come back to the next line 2. Good. And then when we are done with this function 2, then we pop one more time, then we get the address of next line 1. So we can come back to the next line 1, and then we can finish function 1 perfectly. So whenever we call a new function, then we have to push the address of the next line. Okay, and then whenever we call function again and again, then we push. And then when we are done with one functions, when we finish that function, then the last in of this tag will be the place, the place that we have to come back. Okay, so the stack is the perfect structure to handle this kind of informations. Okay, so now let's try to understand a stack as an abstract data type. So far we talked about some figures, right? So we talked about how it works. So let's talk about stack as an abstract data type. So first, data. Data is a finite ordered list with 0 or more elements. Okay, so we can use array or we can use some other implementation, but basically in the abstract data type, the data is a finite order list with 0 or more elements. Okay, and operations. So basically we have to create a stack. Okay, so empty stack. And we can give the maximum size as a parameter. So if we use something like an array, then we have to, we have to give the size to allocate memory space. And then obviously we have a push and the pop operations. So these two operations are kind of the most important operations. So first push. So when we push, then we have to pass a stack and item. Okay. Or if think about a class, then we don't have to pass these tag informations because when we declare one instance, then that instance is, since the member function push knows which stack we are talking about. Okay, but anyway, we are not talking about the class. So in abstract data type, the push needs some information about the stack and then an item. So we want to push this item into this stack. And then if the stack is full, then there is an error. So basically in this push functions, we have to check if the stack is full or not. Otherwise, we push. And the return type is void because we don't return anything. And the next, pop. In this pop operations, we don't pass any items. Okay, we will get one item from this stack. So the return type is an element. Basically, the type of item is element. So the return type is element. Okay, and then as a parameter, we just pass the stack information. Okay, and if the stack is empty, then it is an error. Otherwise, we will get one element from the stack. Okay, and depending on some implementations, there are different definitions of this pop. Sometimes pop will just read the top element and it doesn't delete that element. But in this case, the pop will read that and then it deletes the top elements. Okay, read and delete from the stack. Okay, and we have a couple of more operations. First one is full and second is empty. So basically is full as checks if the stack is full or not. Okay, return type is boolean, and is empty is checking if it is empty or not, and also the return type is boolean. Okay, from this slide on, we'll talk about some implementations of a stack. So there are a couple of different versions. So from the naive implementations to class-based implementations. Okay, so first one is array-based implementations. And this one is really knife, and this one is basically from the textbook, but this is not recommendable. But anyway, let me explain what it is, okay? We will implement this stack, as you can see with this figure, and we have a structure, okay? So in this structure, we have a key, and if you want, we can have other elements, and element is kind of the structure data type. And we have an array of this element, and the max stack size is the size of this stack, and then the top is integer, which is -1 initially, okay? So it is a global variable. So whenever we push, then top will increase. Okay, so if we have one element, then top will be 0, and if we have two elements, then top will be 1. And whenever we pop, then top will decrease. Okay, that's how we implement this one. So it's a simple. Okay, that's a simple. Yeah, in the previous slide, yeah, there was a simple implementations, but we don't like that because the key, the integer variable top is not attached to the structure, the stack, right? So when you implement that, then you know this top is connected to the structure, the stack. But like 1 month later, when you read your code again, then you might get confused because the integer variable top is not strongly connected to the stack. Okay, so this implementation is better than the previous slide. So we have the same kind of definition for the element. Okay, so far the same thing, but instead of having this array and the top separately, we have another structure. In this structure, we have element pointer variable stack, and we will allocate memory space later. And we have a maximum size and the top. So this stack and top, they are connected as a member of this another structure stack. Okay, this is a better approach. Okay, so with this better definition of a stack, then the operations can be implemented in this way. So the first one is the create S. Okay, when we create a structure, a stack, okay, then as we have seen in the previous slide, the stack has an element pointer stack, right? So we have to allocate memory space for that. And when we create a stack, then we have to give the maximum size. So with this maximum size as parameter, then we allocate memory space with malloc. Okay. So the first line, stack pointer S, is a pointer, and it gets it is pointing the memory space for one stack. Okay, so that S is a pointer pointing the one stack, the memory space for one stack. And actually the stack, the information will be in the next line. So S stack will point some memory space for max stack size times size of element memory space. Okay, so we allocate memory space with this many bytes, and then S stack will point to that memory space. Okay, so S stack is actually pointing the stack structure, and S max size will get the max size, and S top is initialized as -1. Okay. Okay, then when we have a stack structure with the create S functions, then we can push and pop, right? So when we push, then actually we have to check if it is full or not. So we call it's full. Then if it is full, then we print out some error message and we just quit. Okay, and then else, it means it's normal state, it is not full. Then we increase as top. Okay, top variable. We increase top variable, and then we assign item. And item is a structure instance, so assignment will copy all the elements from item to this as a stack array. Okay, so item might be some simple numbers or some simple character or something, or it could be a structure instance too. So we can push one structure instance into our stack. Okay, so it's a simple. And let's look at this pop function. Okay, and then we pass the structure, the stack structure pointer, and we check if it is empty. If it is empty, then we print out error message and we quit. Otherwise, we return as a stack and as top minus minus. So we read the top element first, and then we decrease as top. Okay, we decrease this top variable. So after reading, so we will return this element from the top. Okay, and then after reading that, then the top variable will decrease. So in this case, we are not actually deleting the top elements, but top variable is pointing the lower one, the below one, right? So that actually the top one will be considered as a garbage, even though we are not deleting that element from the stack, but top goes down. Okay, that means this top element is just garbage now. Okay, next ones is full and is empty. So is full is a simple. Okay, we just check if top variable is equal to max size minus 1. Okay, this one is top goes from 0 to max size minus 1. So if these two are the same, then it returns true. It means it is full. Okay, otherwise it is false. Okay, it's a simple function. And next one is empty. So if the top is negative, the top variable is negative, then it is empty. If top is 0, then we have one element. If top is 2, then we have 3 elements. Okay, so if it is negative, then we return true, which means it is empty. Otherwise, we return false. So far, we talked about the implementation of stack with structures. Okay, so when we have a structure, then the structure has all the data variables, and we implemented the functions separately. So these functions are separate from the structure, and these functions will get the structure information as parameter. Okay, so that's how they are connected. But when we implement this stack with a class, there is a better way. So in the class, we will have all the data variables in the class, and at the same time, we will have all the functions in the class too. Okay, so instead of having data and functions separately, in the class, we will have data and functions in the class. Okay, so let's take a look at these implementations. First, class. So in the header file, in the stack.h, we have an element. If you want, this element could be a structure, but in this example, we use just integer. Okay, so element is just a simple integer. Okay, and then in the class stack, we have all the data variables as private members. Okay, and since these are private, then from the client functions, they cannot have any access to these members. So they need functions to have an access to these variables. And we will have all the operations as public member functions here. Okay. Okay. So since we have a class for stack, then we have to implement all these operations. First one, constructor. Okay, so if the functions are really simple, then these implementations can be in the header file. Or if the functions are kind of too long, then we can have this implementation in the CPP file. But anyway, so first one is constructor. So constructor means when we declare one instance of stack, then we have to have some memory space, right? And we have to initialize the top variable. So top is -1 and max size will be the parameter max stack size. And then, in the C style, we can just use new. Okay, so we allocate enough memory space for this stack. Okay, now the stack variable is pointing our stack. Okay, like this figure. And we have a destructor. In this destructor functions, we delete the stack. So in the constructor, we allocate memory space, and in the destructor, we deallocate memory space. And how about the push and pops? So basically, the implementations are really simple, really similar to the implementation with the structures. Okay, so return type is void for push functions, and when we implement some member functions, we need this stack, colon, and colon. Okay, so the reason why we have this stack, colon, colon is that sometimes we have many different classes and with the same name for the member functions. Then with these resolutions, then we know which class has these functions. Okay, so this push is a member function of a stack, and we have one parameter item. So when we implement this with the structure, then we have to pass the stack information too. But in class, we know I'm already the stack's member function, so we know which stack we are working on. So we don't have to pass that information. So just item is enough. And in the function, we check if it is full or not. Okay, and otherwise we copy this item to the stack. Okay, so stack is a private private data variable. So item can be copied to this array. Okay, and in the pop functions, we don't have to pass any stack informations because we already know that, and the return type is element. And within the functions, we have to check if it is empty, and if it is empty, then we return something like 0. Okay, otherwise we have to return the stack and top minus minus. So by that, we return the top element, and then we decrease top. Okay, as before, we don't delete, but it is actually logically deleting. And we have to implement its full and its empty functions, member functions. Okay, and the return types are booleans. Okay, and then you don't have to worry about this constant keyword. Just ignore that. If you don't like, you don't have to use this constant. Okay, so ignore that for now. Okay, and then we return for its full function. We returned top equal max size -1. So basically, the implementation is almost the same as the implementation with the structure. But since we are using class, then we don't need the structure information here. And this empty can be implemented real simply too. If top is -1, then it's empty. Or if top is less than 0, then it is empty. Okay. So here is a practice slide about the stack. Okay. So we are implementing this stack with the class. Okay, in the main functions, we declare one stack pointer variable stack and allocate memory space for that stack. So we have 5 elements. We can have 5 elements in our stack. Okay, and then we call a stack print. Okay, we didn't talk about these print functions, but you know how to implement print functions. Okay. So let's assume that we have a print function, and we push one element and we push another one and we print. Okay, so you have to implement these print functions. And then we can call pop functions so that we can see what we have there, and then we can print the elements. And this is a stack header file. Okay, and the element is a structure. In the previous slides we used just integer for element, but as I said, element can be a structure. So in our stack, one element is just one instance of structure. And in the class stack, we have a top and max size and the double pointer, the element double pointer stack. Okay. And in the public functions, we have a constructor, and we have two different types of constructor. So just the default constructor, and the second constructor gets just one integer value. And if we have some specific number for the structure stack, then we will call the second constructor with the fixed number of size of the stack. Otherwise, if you don't have a specific number, then we will use some default number. Okay, and we have this structure, and we have it's full and it's empty, and we have a push and pop functions. And push pop will pass the element pointer, and it will get element pointer. So instead of passing the structure one instance itself, if the element is really a big structure, then whenever we pass one element, then we have to copy everything. So it takes a lot of time. So instead of that, we just use a pointer. Okay, that's better. And this implementation is slightly different from the previous implementations. Okay, and then we have print functions. Okay, so in the stack2.cpp, then we have to implement the constructor and the push and the pop. And this implementation is almost the same as the previous implementations with the class. Okay, but in the previous implementation, we just used the structure instance directly. So structure, the element is a structure. Okay, so we use the structure instance. So to remember, when we assign a structure to another structure instance, then we copy all the members, right? So what if this element is really complicated, complex, large structure? Then whenever we call these functions, we have to copy everything. That takes a lot of time. Okay, so in the computer, whenever we need any access to memory space, then it takes a lot of time. So we have to minimize that number. So instead of passing the structure instance, we pass a structure pointer. So we don't have to copy all the members. Instead, we just copy the address. Okay, so in this stack, we just manage this the address of these structure instances. Okay, in the main functions, we declare one stack pointer stack, and we allocate memory space with the 3 elements. Okay, so the maximum size is 3 for this stack, and we have element pointer item. So item is just a pointer, so we need to allocate memory space with the new element. So now item is pointing some memory space in the heap. Okay, and then we assign some information to this memory space. Still item is pointing that, and we push this pointer to our stack, so that in our stack we just manage the pointers, not the item itself. Okay, so this item is still pointing the memory space from the heap, and we just pass the address of this memory space. Okay, then the stack will get that address. Now we allocate the memory space again, and then the item is pointing another memory space. Don't worry, we don't have a memory leak problem here, because a stack, the first element of the stack is pointing the first memory space. Okay, and now item is pointing on another memory space, and we assign some information to that memory space, and then we push this pointer. So now the stack has 2 pointers. Okay, and then we print out. So you have to implement this print function by yourself. And if we call these pop functions, then item will point that memory space. Okay, so we don't pop one structure here, we just pop a pointer. So item will point to that memory space. Okay, if item is not null, it means we had something there. The stack was not empty, so we got 1. Then we print out some information here. And then we call print function one more time. So then you will see the difference between the first call of print function and the second call. Okay, I understand these implementations might be headache to you guys, but you have to read the code and you have to understand what's happening. You have to see the difference and you have to understand how it goes. Okay. If you get lost, then at least you have to tell me like, oh, I'm lost at this slide. That's enough.